Hello, hello. Hope you can all hear me and hope you can all connect as well. Let me know in the chat. Let's see who is in the chat. I'm going to check the stream very quickly just to see who is in here. But say hello. Let's see how you're all doing. We've got Abdul Rahman already. Yeah, good evening, Abdul Rahman. We have Moonlight as well. I've been speaking to Moonlight and Path. Anybody else in the chat before we get started? Really excited to deliver this lesson for you today. And I'm looking forward to hearing from lots of you as well and having a lot of contribution as always. So just drop me a message in the chat. Let's see who is here. And I am going on YouTube very quickly as well, just to see how many people are live with us so far. So say hello. We've got 10 people watching, but only 3 people. So say hello. We've got 10 people watching. Ah, Zara. Yeah, hello, Zara. Anybody else in here? Yeah, say hello. Nice. We got Toto as well. Yeah, good stuff. All right, guys. Thank you for responding in the chat. The more we respond in the chat, the more entertaining the lesson is for you, for me, and for everybody involved as well. So let's try and keep it up in the chat there as well. Okay, so I am looking on the YouTube and I can see we've got 11 watching now, so that's great. And Aesthetic Taurus, excellent. So I'm going to get started and let's go, let's go. Before we get started, I want to tell you a little bit about myself. So I am Manny. Most people call me Manny at work. My full name is Emmanuel, and I have been teaching for over 5 years. I've got over 5 years teaching experience, especially in chemistry. And 2 of those years, I was head of chemistry at a school in East London. And I also worked as a study club coordinator, which just means helping Year 11s to really achieve their targets. And I studied chemistry at Imperial College London, and currently I am doing a master's at King's College London. So hopefully you've heard of those places as well. But all I want you to know is you are in safe hands. So let's zoom back out and let me let you know that this is a free lesson. Okay. So what you can do is share this lesson with your friends. No problem whatsoever. So if you want to, just go to the YouTube, go to the stream and click into the address bar and send it to your friends right now. Yeah, let me know if you're doing that in the chat, but send this stream to your friends. Yeah, they're more than welcome to join. So just send the stream over to your friends and hopefully they can join us as well. So in the chat, let me know who has already sent this to their friends. Let me know who has sent these to their friends already. Okay, perfect. So moving on, I'm going to get started with the lesson for you. And just to let you know that if you are in the chat, use the workbook to help you. If you don't have access to the workbook, that's absolutely fine. You can still engage in the lesson using the resources just from the video alone. But the workbook is fantastic if you have it. Okay, so before we move on, I want to test your knowledge from GCSE. This lesson is going to cover a lot of GCSE content. So it's mainly structure and bonding, which is a foundation for A-level chemistry. So I chose this topic because it will help you anyway, whether you sign on to our main course or not. But the whole point is, please sign up to the main course. It'll be fantastic. And I can see Toto, Zara, a few people in here already. It'll be lovely to meet you in the main course as well. Okay, so my challenge for you is firstly, what is, so challenge over here and challenge, what is this phrase? And what do you remember in the chat for all of these types of bonding? You can pop anything you want in the chat. We'll see how we're getting on. Okay, so that's a challenge for you. What does that phrase mean? But tell me in the chat, what do you remember? Yeah, excellent, Moonlight. Great interaction so far, Moonlight. I appreciate that. Toto, yeah, so Van der Waals is V-A-N, Van der Waals. That's absolutely fine. That is something you're going to look at in more detail in year 12. But at the moment, let's focus on the GCSE terminology. But you are correct. You are correct. Okay, perfect. So we have already, some people are saying that for ionic, we have metal plus a non-metal. That's absolutely correct. Yeah, fantastic knowledge so far. What else have we got? Our text, hello text. Metallic is just for metals, so here is metals only. Yeah, good stuff. Tech, nice to have you in the chat as well. Metals only. And did anybody mention anything about covalent? So covalent would be for non-metals only. Yeah, excellent. Non-metals only. So when you get to, or you are already in year 12, I would say, What you need to, we've got Klaus Hybrid as well. Hello, Klaus Hybrid. What you need to be clear on is chemistry is the science of specifics. You need to be super specific in what you are telling me in terms of your response. So I can see already aesthetic there. You've got great knowledge using the keyword lattice. That is a specific bit of language there. Who can tell me what lattice means? And it'll be lattice of ions. Yeah, great stuff. And ions are important here because ions are formed either by losing or gaining electrons. So that happens in ionic bonding. So let's pop that down. Yeah, really good knowledge in the chat, by the way. Hello, Godiva. You haven't missed anything. Yeah, so lattice is just a regular repeating structure. So I'm going to switch out. Let's go for green. I love a bit of green color there. So lattice is just a regular repeating structure. Okay, so it's a regular repeating structure. So we have ions repeating in a regular pattern over and over again. Okay, so what you need to know is the key phrase electrostatic force of attraction. What is that? What is an electrostatic force of attraction? So in ionic, Zara, you are absolutely correct. Yeah. So in ionic, we have electrostatic forces of attraction. Electrostatic. Yeah, I see the chat is going off, which is really good. Forces of attraction. Between oppositely charged ions. So that would be the definition you would write down for A level, because that's very specific. Yeah, and it's ionic, so it's all about ions. But let's see what we put in the chat. The attraction between ions. So you are correct in this case, but overall electrostatic forces of attraction are attractions between opposite charges. That's very important. Between opposite charges. So depending on what these charges are or where we are seeing these, yeah, excellent. It doesn't always have to be ions. We've got Xeno edits. Yeah, it doesn't always have to be ions. It can be between nuclei, for example, or it can be between the nuclei and the shared electrons. It depends on the context. So I'm going to make it clear for you in covalent bonding very shortly. And Zara, the word intermolecular force always has the word weak in front of it. The phrase intermolecular force always has the word weak in front of it. Hopefully today will help you to tell the difference between when to use these phrases. So please make sure you're paying attention as we go through. But let's have a look at covalent. So for covalent, for this year, you are sharing electrons instead. So electrons are being shared. It's the sharing of electrons. Okay, and moving on, you have different types. You've got, let's change the color there. I'm going to go for the black. So you've got two types we need to know. You've got simple covalent, which are molecules we see all the time. Simple covalent or simple molecular. Yeah, I like the fact that somebody used that as well. So these are small molecules, or you have giant covalent, which uses lattice of repeating atoms. Yeah, we've got some examples that people are putting in the group there as well, but this here is a giant structure, so they have slightly different properties. We'll look at that in more detail very shortly. Before we move on, I want you to know the exact definition here for covalent bonding. It will be electrostatic forces. So again, these are attractions between opposite charges, but what are the opposite charges for covalent bonding? These are electrostatic forces. Let's write quickly, but neatly as well. So electrostatic forces of attraction between, in this case, between shared electrons. So you have electron pairs being shared electrons, and the nuclei in between them as well. Okay, and the nuclei. So I'll show you a diagram to help you make sense of this. So you've got one shell, another shell, for example. You've got electron pairs in here, and you've got positive nuclei here. And let's tidy up my diagram a bit so it's clear. So the middle of this here is positive, and in green, this is what the covalent bond is. The covalent bond is the attraction between the positive nuclei, and the shared electrons. Okay, and in the chat I can see people are giving me lots of examples, which is great. So I have, what do I have here? CO2, hydrocarbons. Yeah, perfect. Those are simple structures. And then somebody's given diamond and also silicon dioxide as examples of giant covalent. That's perfect. Okay, so moving on, let's have a look at metallic just to finish up our recap. So it's metals only, and we have the structure involves cations. In the chat, can you let me know what a cation is, please? What is a cation? So cations in a lattice, so cations in a regular repeating structure with a sea of delocalized electrons. This is going to be important very, very soon. Also, I have to let you know, if you stay till the end of the lesson, there is a quiz, a bit of competition. I want to know who is the sharpest in terms of their structure and bonding. So we have a quiz at the end, and Dobby's in the chat for whoever wins. So we'll have a look to see who makes it till the end and who wins that quiz. Okay, so we've spoken about that there. We also need to know, we also need to be aware of alloys. So alloys are mixtures made up of two or more elements where at least one of them is a metal. So alloys you need to know about there as well. And quickly here, let's see the chat. And yeah, a cation, I remember it because it has a T in there. So a cation, because of the T, reminds me that it is a positively charged ion. Okay, so cation is a positive ion because of the T looking like a plus sign. That's how I remember it. Okay, so again, electrostatic forces have come up again. So remember, all of these are different types of electrostatic forces. It just depends on what they are between, and that's what gives us the name of the type of bonding. So electrostatic forces of attraction between shared cations, sorry, and delocalized electrons is what we call metallic bonding. Okay, so let me know if you have any questions before I move on to the next one. Hopefully, yep, my head is in the way, so I'm going to get rid of this and pop it below delocalized electrons. So in the chat, let me know. We have a good diver as well. Flo, yeah, welcome, Flo. Yeah, keep it going with the contributions in the chat. And I'm going to move on because I haven't had any questions in the chat so far. So swiftly moving to the next part here. Now we're going to think about the properties of these very quickly. So we spoke about lattice already. You can see we have two different models representing our lattice here. In the chat, let me know. So you can see I've got two lasers here, but you can see here this version and that version over there. What is the difference? What is the difference? And why is one better than the other? Okay, so change from the laser to the pen. Okay, perfect. Yeah, so what is the difference between these two models? Both of these are representing. Yeah, perfect. So that's the ball and stick. Moonlight, great knowledge from you there. Ball and stick here. Ball and stick. I'll get rid of the dashes in between. We don't actually need those. Okay, and the other model, yeah, great stuff, aesthetic. So this one is suggesting we've got empty spaces between there, but that's not absolutely correct there. And how is the polarity of the molecule determined? And ex-Zeno edits, that's not something we're going to cover today, but those are something you can do, an experiment you can do that will tell you the polarities there. But the most electronegative element is fluorine, and you can use that as a datum as a way to compare the rest of them against. But that's not something we're covering today, so I will keep to the content for today. But that's a great question. Okay, so moving on, when we have a look at this one here, this one suggests that all of the ions are touching, suggests they all touch, but that's not true as well. So there are some inaccuracies with these models here. However, you need to realize every model has its downfalls, and what you need to use is your kind of reasoning to see what you're looking for with the model, and every model has also its pros associated with it as well. So the ball and stick suggests the bonds are physical, which isn't true. Exactly, Godiva, well done. And this one here, You can refer to this one as ions as spheres model. Yeah, but it doesn't have a specific name. Yeah, but you can look at it and see that the ions are represented as spheres, which is not completely true. Yeah, Yodit is absolutely correct. Make sure you like the video, people, and welcome Yodit. So I'm going to go nice and quickly. Here we know we have a lattice of oppositely charged ions here. Oppositely charged ions. Okay, I'm writing a bit quicker, so if you can't see what I'm writing, let me know. But I'm clear. Sorry, I'm aware it's clear now, but if it's not, let me know. Happy to slow down for you. I just want to get to the end so we can have a go at the quiz. I see lots of good knowledge in here, so I want to see who is good here. Yeah, and Godiva, yeah. I'm good with names, hopefully, and if I get your name wrong, just let me know as well. Okay, so we have lattice of oppositely charged ions attracted to each other in all directions. In all directions. Okay, that's very important. Lots of people do not realize that this is 3D. You need to be aware, especially at A level, that this is 3D. Okay, in all directions. Okay, what else do I want to tell you here? We've got strong electrostatic forces of attraction between ions. You remember that already. So the melting point for all ionic substances is always high. They have high melting points. Okay, high melting point. Yeah, exactly. High melting point. Who said that? Aesthetic. Excellent. Okay, because we have lots of ionic bonds, aka lots of electrostatic forces of attraction between oppositely charged ions, and we require a lot of energy to break them. Yeah, well done. A lot of energy required to break those bonds. So the melting point is always going to be very, very high. What about the electronic conductivity? Who can tell me about electronic conductivity of these? Anybody have any clues in the chat? Yeah, I'll have a wait to see what we say in the chat. Any clues? They are, but are they always? Yeah, Zara's correct there. Are they always able to conduct electricity? So Zara, you're absolutely correct. When do they not conduct electricity then? When do they not conduct electricity? Yeah, perfect. Yeah, I like the fact that aesthetic you mentioned ions. Lots of people get confused and they start saying different things there. So Moonlight, you are correct as well. So not as solids. You are not getting any conductivity here as solids. That's because the ions, as you can see in our model here, the ions are locked in place. The ions have nowhere to go. They cannot move. They are locked in place. Okay, I'll try and not get in the way of my head this time. But they can conduct electricity. Let's swap over to green so it looks very different. Only when molten. Tell me in the chat, please, what does molten mean? And let's write it clear so you can see. What does molten mean? And what does aqueous mean? Let me know in the chat. My head is in the way there as well. Yeah, molten means melted exactly. So when it's a liquid, and what does aqueous mean? Aqueous, if you speak a different language like Spanish, you will know that this is very close to water. Yeah, exactly. So it means dissolved in water. You have to be very specific. Aqueous means dissolved in water, because at A level especially, you'll find out there are other solvents you can use. So you need to be very specific. Aqueous means dissolves in water. And there's another solvent, for example, ammonia. So if something is dissolved in ammonia, you wouldn't say aqueous, you would say ammoniacal instead. So you've got clear specific terms that we've got to stick to. Okay, so I'm going to move on. When we have these in this state, molten or aqueous, the ions are now free to move. Free up the ions, so ions free to move. And you need to make sure my head is not in the way. So ions are free to move and carry charge. And you need to say this specifically, and carry charge. We do not teach the IB, unfortunately, Godiva. We do AQA and we do OCR, and carry charge through the structure. Carry charge through. That keyword is important, through the structure. Okay, so that's it for ionic compounds. That's it for ionic compounds. I'm going to move swiftly on. I just want to see if people have any more questions before I move on. But I really love the chat. W's in the chat there. You guys are super smart, super clever. I hope to see lots of you on my main course. Yeah, don't just leave your brains to go away and not join us here at MES. Would love to have a lot of you on and help you smash the top grades with our help and support as well. So W's in the chat for top knowledge here. You guys are doing a great job. Okay, how many lessons are there a week? You're going to have 2 lessons per week. So that will be hopefully enough to supplement what you're doing in school as well. And do you get notes for my Headspace? Yep, we are also running it's a bit of a secret, but we're running a kind of a resource very similar to what you might have in a textbook, where it goes through all the main topics for you with clear notes and ways for you to practice. Okay, moving on. We're going to look at covalent substances now. We're going to look at covalent substances. So what you need to be aware of here is we've got the 2 types. So I've split the screen into the 2 sides there. And we focus on the small molecules. The small molecules there have low melting points. And this is where lots of students have misconceptions around the reason for this here. So again, your language is very important when you're talking about these here. So I'm going to give you a model. We'll use water as a model. And you're going to learn about what we call intermolecular forces in a bit more detail. Okay, but this here is a simple example of this here. Do not get confused though. Be aware that inside the molecule, we have strong covalent bonds. Yeah, we have strong electrostatic forces between the shared electrons between oxygen and the hydrogen and the nuclei of the 2. Do not get that confused. But in between the molecules, because these are simple molecules, let's go next there. They're very simple structures. In between with the dashed lines, I'm going to change the color so it's very clear. And what color are we going for? We're going to go for blue. So in between each molecule here, we have weak forces. Okay, we have weak forces there. And we call those weak intermolecular forces. Yeah, this is where lots of people make mistakes here. So I'm just taking my time to make it clear. Be aware that the covalent bond is strong. Yeah, the covalent bond is still strong. However, the reason why they have low melting points is down to the weak forces between these simple molecules. So here, not a lot of energy is required. In this case, we're not breaking bonds. When we separate these, we are overcoming forces is required to overcome those weak forces. Yeah, to overcome the forces. I always speak about these forces in this way so that the language is clear. We talk about overcoming forces and breaking bonds. Yeah, just so it's very clear. And these have no electrical conductivity whatsoever in any shape or form. And that's because the charged particles are all locked up. They have nowhere to move, no electrical conductivity. And if you can tell me, let's tidy this up. What is electricity in chemistry, please? In the chat, what is electricity in chemistry? So electricity, what is it? In the chat, let's see what you guys are saying. Yeah, low melting and boiling point. So I can add that in there as well, just to be super clear. Good shout from Aesthetic. Yeah, well done. And boiling points as well. Okay. Yeah, excellent there. Zeno Edits. I'm not sure how to say your name properly, but excellent points from you as well so far. So the movement of charged particles. You need to be clear which charged particles are moving, depending on the type of structure and bonding you are looking at. So charged particles here. And sometimes it could be ions, sometimes it could be electrons. Definitely not protons, because protons do not move around. Yeah, protons are stuck in the nucleus. And Aesthetic Taurus, I hope everything's okay. If you have any questions, let me know. Okay, so moving on, we're going to talk about diamond first. So I'm going to pop this one here. But in the chat, give me some more examples, please. People have mentioned silicon dioxide as examples of giant molecules. Give me some other examples in the chat as we talk about diamond. So in diamond, I use this word and I stress it all the time, each, you need to say each. Yeah, so carbon, each carbon is bonded to 4 others. That gives it what we call a tetrahedral shape. You will come across this here in your time in year 12 chemistry. Tetrahedral just means that the center point has 4 other things connected to it. Okay, yeah, perfect. There's edits here. Fullerenes will take. Fullerenes we need to know about for sure. We've got some really nice other examples there. Nanotubes as well. Nanotubes as well are quite important. Okay, and then because of this here, diamond has no electrical conductivity. Let's make that clear as well. No electrical conductivity. And what else do I want to say? Because of this rigid structure where everything is connected to 4 other carbons there, no free electrons exactly. Yeah, Buckminster balls are types of fullerenes. Excellent, Habiba. Good contribution, Habiba. Keep it going. So the diamond has a rigid structure because of that tetrahedral form, and that means it's very hard, and it is used in cutting tools, for example. Yeah, it's used to cut other materials. Okay, so that's it. We need to realize though that for all of these, let's try and get this nice and neat for you. Okay, that is not so neat. And let's go here. And let's finish up down here. Okay, perfect. Yeah, so I'm splitting these two up, but the giant molecules all have high melting and boiling points. Yeah, they all have high melting and boiling points. And that's because everything is connected, even in the next example we're looking at, which is graphite. Even though graphite has each carbon, again, notice how I'm being very explicit in my language, each carbon, if you don't say each carbon and you just say graphite has 3 carbons or graphite has 3 bonds, you will not get the mark. Each carbon is bonded to 3 others in graphite, and what that does is it forms layers. It forms hexagonal layers. So you get layers of repeating hexagons, but it still has a higher melting point. Not as high as diamond, but you still need to break all of the carbon bonds because remember, everything is giant and connected. So to get it into its simplest form where the particles are as far apart from each other as possible, you need to still break bonds. That's the difference between the small molecules and the giant ones. The giant molecule, everything is connected mostly. In the small molecules, not really. You've got smaller molecules with weak forces there. So be very clear on that. Yes, so swiftly moving on, we have 1 delocalized electron per carbon. 1 delocalized electron per carbon. Just making sure my head is not in the way. Okay, so because of this here, they can conduct electricity because the electrons can move through the structure, and carry that charge. However, because of these layers, so I'm going to use a different color so we do not get it confused with the bits for diamond. I'm just going to use this space here to talk about what the layers give us. So because of these hexagonal layers for graphite, I'm still on graphite here. Just for space, I'm going back up there. So for graphite, because of these layers here, the layers have weak intermolecular forces between them. So weak, I need to be careful to fit all of these here. Yeah, weak intermolecular forces between the layers. Okay, so because of that, the layers can slide over each other. So they can slide over each other. And yeah, so I wouldn't say weak forces of attraction, Zara. I would use the keyword weak intermolecular forces. I'll use that key phrase so you can get all of the marks. So they can slide over each other. And that's what makes graphite soft, even though it still has a high melting point over each other. And this is why we use graphite as a lubricant in industry. It just helps reduce the friction between two surfaces. Let's write that clearer. Okay, so in the chat, let me know if you've got any questions or any knowledge you'd like to share with us as well. Always welcome to see what people want to share in the group, in the chat. And can we just call it intermolecular forces? You have to say weak intermolecular forces. However, we're going to move on, if you're in the main course, to talk about the different types of intermolecular forces. So in intermolecular forces, you've got different types. We can talk about those as well. And Xeno edits, absolutely banging there. Yeah, they're sp2 hybridized in graphite and sp3 hybridized in diamond. However, that's not something we're going to cover today. It's something we get to cover in the main course if you signed up. But amazing knowledge from you there, Xeno edits. I love it. Okay, so moving on. Can you fill the gaps here, please? Fill out the gaps. I'll give you some time. I'll put some numbers here so you can tell me what it is in the chat. 1, 2, 3, 4, 5. Okay, in the chat, let me know what is going for each number. And Xeno edits probably saw that online. Don't worry about it. It's not expected knowledge at the moment. It is knowledge we will cover in the main course. Do not worry too much about that. So I'll let you know what you need to know for this free lesson, but do not stress. I'm just acknowledging people's outside knowledge, which is quite impressive as well. Okay, so in the chat, I should be seeing stuff like this here. I should have 1, for example, if you think, so molecule consists of, the first one's easy, so I'll put it in the chat. Yeah, so in the chat, you should say number 1 is molecules, for example, and let me know how you're getting on. So here we would have molecules, and then we can cross it out. Yeah, perfect. A molecule is a particle in which the atoms are held together by not electrostatic bonds. Yeah, we don't use electrostatic for bonds. So it would be covalent there. Yeah, the bond is covalent. Okay, number 3 would also be covalent. So we've got covalent twice for that reason. So tick covalent off there, tick it off there. Ah, that's all right, Moonlight, don't worry. I like your engagement. Yeah, Aesthetic Taurus is cracking on there. So they said it is defined as an electrostatic force of attraction. So electrostatic force of attraction. And do we have attraction there? We do. So I'll take electrostatic away. I'll take attraction away as well. Excellent. Of shared, have we got number 6? Yeah, a shared pair of electrons. So electrons always come in pairs in chemistry. If they're not, then they're not so stable. Shared pair of electrons to the positively charged nuclei. Remember, the nucleus is always positive. Excellent. So we get rid of positively, we'll get rid of pair. And have we got electrons? We've got 3 more here. We got enough. So simple substances have low. Yep, we've got low there as well. Low. This is because there are weak. Which one there? We're missing intermolecular. We don't have that there. So intermolecular. Yeah, good spot. Intermolecular. Remember, you always say that phrase together. Yeah, that word is missing. Good spot. Aesthetic. And then the last one, there are no free electrons for simple molecules. No free electrons. So no way we should be expecting the electricity to be conducted there. Yeah, really, really well done. Also great stuff on aesthetic for spotting the missing word there as well. And what's the difference between intermolecular and electrostatic? Yeah, good question. So intermolecular. Inter means between. So if you talk about international sports, you are having sports between nations. Yeah, between England and Spain, for example. International. So inter means between. Molecular just tells you it's molecules. So as I said before, it would be the forces between molecules. So if I drew this here as an example, to represent molecules of water. These molecules of water all have some forces between them. Okay, that's intermolecular forces. When we talk about electrostatic force here, so let's go back. Electrostatic. This one is not as clear to break down, but electro is to do with charges. Okay, and then static just means, you know, stays the same, doesn't move around, but that part is not so important. The electro part reminds me that these are forces between, or attractions between, opposite charges. So that's how I remember these. Hopefully that is helpful for you there, Zara. Okay, so we're going to move on and very quickly try to identify these different substances here based on our knowledge. I'm going to go through these super quickly, super quickly. You know already that silicon dioxide is a type of giant covalent structure. Diamond is as well. Neon, however, is none of them. None of them. Who can tell me why? Why is neon none of them? We've got P4, which is going to be one of the important allotropes, so types of phosphorus you're going to see. And P4 is a simple molecular substance. And because we've got metal and non-metal here, we know that this is going to be giant ionic. Yeah, so Zara, it is just an element. It is just an element, but some elements exist as molecules. So for example, O2, if you look at O2, that's going to be two oxygens joined up. If they're joined up, that makes it a molecule. So this is a molecule, but it's still an element. Molecule plus elements. So it's still a covalent substance there, O2. It's covalently bonded because it's between two nonmetals. Yeah, perfect. But neon is just one atom. So we call this one here monoatomic. Monoatomic. Okay, there's only one atom there, whereas oxygen is diatomic. There are two atoms, and because those atoms are the same, it's still an element. It's only made up of one type of atom. Okay, so you need to know the definitions of molecule, element, compound, atom. All of these are important before you start year 12. Okay, so swiftly moving on, you're going to hear that phrase a lot. I say it all the time. We're going to finish up with metallic bonding. Metallic bonding is quite easy. Okay, so for this one here, we know that these are organized in layers. You can see that already, organized in layers very clearly of cations. So we need to label our cations. If you've got a workbook, make sure you're labeling your cations. You've got a plus on all of these. These are all cations. I'm just looking at the chat. Yeah, excellent. Great knowledge from you there. So yeah, O2 is simple molecular, correct? Yeah, and remember, a molecule is when you have a substance made up of two or more atoms, okay? When those atoms are different atoms, then we have a compound. When those atoms are the same atoms, we have an element, okay? So here we've got layers of cations with a sea of delocalized electrons. So we need to label our delocalized electrons as well. And I'm writing quicker and quicker, so you can see the quality is going down. But let me know if you can't see it. I will write it out clearly for you. So let's pop in some delocalized electrons here. Okay, so the outer shell electrons in the metal are then free to move around to conduct electricity. So here can conduct electricity, but also you can tell me in the chat what are metals known for in terms of being great conductors of. So can conduct electricity, and I have to make sure we've got enough time at the end there. So can conduct electricity and heat. Excellent. Yeah, so heat as well, and that's because the delocalized electrons can carry kinetic energy through the structure, or the charge as well through the structure. Okay, so very quickly, thermal and heat as well is a great one there. Before we move on, I'm going to tell you about alloys very quickly. And alloys, you should know, aren't so organized as we have over here. So the alloys, as you can see from my quick sketch there, will give you different sized atoms in the mixture. So an alloy is a mixture, different sized atoms. And what happens is these will disrupt the layers that we had before. You can see it's not so organized there, and they're going to be stronger. They're going to be stronger than our normal metal, pure metal, because the layers will be harder to slide over each other because of that disrupted shape there. Okay, to slide over each other. Excellent. So I can see that we are strong on this here. So we will be able to get this quiz done, I believe. Let's see how we get on. Before we do that, let's have a look at these examples. So all you can say very quickly in the chat, is it giant ionic? Is it simple molecular? Is it giant covalent? So you can say A is simple molecular, for example. Not necessarily correct. I'm just giving you an example. Okay, in the chat, just let me know. Okay, so we've got someone already super quick there, Zara. Zara says A is ionic. I agree, Zara. This is giant ionic. How do we know? Because it only conducts electricity as a liquid and it has a relatively high melting point. B, we've got covalent. I won't give you the mark for the covalent aesthetic. Remember, at A level, you want to be super specific. You've just done it there. Yeah, good stuff. I see you corrected yourself there. You need to be super specific. Simple covalent. Covalent by itself is not enough. We know that because it doesn't conduct electricity whatsoever in any instance. And C, E you've got for there. E, I wouldn't say E is metallic. I would say E here is giant ionic. Reason being, well, reason being is it does not conduct electricity as a solid. Remember, for ions, it's locked in place. The ions are locked in place for ionic when it's a solid. But for metallic, the ions are, there are no ions there. There are ions there, sorry. The cations are there, but the electrons can always flow through even as a solid. So this one will be giant ionic, but this would be giant metallic, even though the melting point and the boiling point is quite low there. This would be giant metallic due to the fact that it conducts as a solid and a liquid. Okay, so some metals are a bit weird. They have low melting and boiling points. You should know about mercury already, for example. This one here, we got anybody saying for D? D, I would put down as simple molecular. And what would E be? Yeah, good stuff. So E could be diamond. Yeah, it could be diamond, or it could be silicon dioxide, for example. So it'd still be giant covalent. Could be silicon dioxide, could be diamond, has a ridiculously high melting point and does not conduct electricity in any state. And let's finish this with simple molecular. So you can see the difference between these two, even though their electrical conductivity is similar. So here, they both don't conduct electricity there, but the melting and boiling point is what we can use to tell the difference between the simple ones and the giant ones. Okay, great stuff there. Let's now move on. And we have one last task, and I think we've got time. We've got time for a nice quiz. Okay, so I'm going to move on to the next slide, and nearly there. I need to move a bit quicker now. So for substance A, we know that that's giant ionic. Substance B should be simple covalent. And you can see the tetrahedral as quite tetrahedral about this one here, but this one would be giant covalent because of the fact that they are all connected there. They're all connected by covalent bonds. And this will be missing some delocalized electrons. So that would be metallic over here. Okay, excellent. So I want to move quickly because I think you guys deserve the quiz for sure. So we're going to move on. And very quickly, I think I'll skip this one here just for time's sake. We're going to have a look at this one over here. Okay, so very quickly, what we can see is it's asking us why these have low melting and boiling points, for example. First thing is what type of structure, what holds it together, and how much energy would you need to break them. So I will answer them and see if you can answer as we go along as well. So for ammonia, this is simple covalent. I know that because it has two non-metals there. So this will be simple covalent. Therefore, it will contain weak intermolecular forces, and that means that not a lot of energy is required to overcome those forces. Not a lot of energy required to overcome forces, and that is why we find these usually as gases and liquids at room temperature. Next, you've got metal and a non-metal, so this is definitely giant ionic. You've got plenty of ionic bonds. Yeah, perfect. So many ionic bonds in 3D space, which we know are electrostatic forces of attraction. I won't write it down, but it's electrostatic forces of attraction between oppositely charged ions, which is ionic bonding, and a lot of energy is required to overcome that. And I'll use the word break. That's more suitable here. And then last one, we can tell you've got metallic because it's just the metal by itself. So metallic bonding, and you've got many strong metallic bonds between cations and a sea of delocalized electrons. And again, because of that, a lot of energy is required to break those. So hopefully that's been helpful for you to recap a lot of what you need to know for structure and bonding for year 12. And what we're going to do to finish is to celebrate all your learning today by having a go at a quick quiz. So I'm going to try and run the quiz as quickly as I can. So what I need you to do is go onto your phones or go onto your a new tab, but make sure you can still see the screen. If you do not have an external device, a different device, you can still take part in this here. It's not the end of the lesson. This is just to bring the knowledge together. I will narrate the quiz, but if you go to kahoots.it, you will then be presented with this here. So let's get over to this here. Perfect. And I will show you now. You can join my game. So here, you can join this here by putting in the correct game code. So if you put that code in, or if you scan this here, you can join this game. And waiting for everybody to join. Yeah, we've got lots of people in already, which is great. Okay, perfect. We'll wait for a few more. And when everybody's in, we will keep it going. Okay, sweet. A few more. And let me know in the chat if you haven't quite been able to join. And let's see where we are at on the YouTube stream as well. Okay, so I'm going to start this in the next 10 seconds. So if you haven't quite joined, just have a go. Join us very quickly to celebrate all the learning we've done so far. And I will give you a quick intro into how you can sign up with a great code, discount code, so you don't have to pay as much if you're interested in signing up to the main course. Okay, so I'll get this started then, and all the best. Yeah, 4 marks there. Excellent. Nothing to explain here. You guys are super quick. Excellent. So it's a game of speed now. Yeah, it's all about speed, Moonlight. Oh, so this one, odd one out. The reason why the odd one out is diamond is because diamond is the only one that cannot conduct electricity. Nice. Be very careful. This is talking about metals. Oh, yeah. So remember, for metals, it's delocalized electrons, and for ionic bonding, it would be free moving ions when it's molten or dissolved in water. It's changing around now. Yeah, excellent. Nothing to explain. Everybody smashed that one there. Okay, it's looking good so far. Oh, yeah, excellent. Oh, it's changing around again. Yeah, perfect. Yeah, well remembered from the lesson in terms of hexagonal layers. Aesthetic toruses making a charge there. Perfect. Yeah, remember the key. Oh, yeah, you guys are quick. Yeah, perfect. And what a way to spend Friday night learning some chemistry, flexing your chemistry muscles. W's in the chat for the winner. Let's see who the winner is going to be. Be careful with this one, yeah. Yeah, so it's definitely not ions. There are no ions in graphite because graphite is a giant covalent structure, so no ions there. Yeah, nice one, Aisha. Last one. Molten ionic substance. Perfect. Yeah, you guys smashed it there. But in terms of our winners, we've got third place, Mundane. Not sure who that is. Second place, we have Just Moonlight. You made it in the end. And top there, Aisha. W's in the chat for Aisha. Aisha absolutely smashed it. Well done. Okay, so before you head anywhere, just want to take 2 minutes